Mr. GG. We've been talking about plane mirrors and curved. We know that a big DO equals a big DI. A small DO equals a small DI. But not with curved mirrors. Concave and convex mirrors create different sized images.
This is a concave mirror. The reflective side is on the inside of the curve. The focal point of the concave mirror is located halfway between the center of curvature and the mirror. Because of this, concave mirrors have positive focal lengths. If you place an object outside of the focal length, you'll see a real and inverted image. This image can be projected. This image gets smaller as the object moves away. The object and image are the same size when the object is at the center of curvature. If you place an object inside the focal point, you'll see a virtual upright image that is always larger than the object. If you place an object at the focal point, the image disappears completely. This all occurs because light reflects off a concave mirror and converges or comes together at the positive focal point. This is a convex mirror. The reflective side is on the outside of the curve. The focal point of the convex mirror is located halfway between the center of curvature and the mirror. Because of this, convex mirrors have negative focal lengths behind the mirror. No matter where you place an object in front of a convex mirror, you will always create a virtual, upright image. The further the object, the smaller the image. This all happens because light diverges or spreads apart based on the focal point as it reflects off a convex mirror.
This is a concave fire starter. It uses the sun's radiant energy to light a piece of kindling right here at the focal point.
Light enters the fire starter as parallel rays, but always reflects straight through the focal. This concentrates or focuses the light at the end of the fork.
Let's go set something on fire. Thanks for stopping by. Remember to like and subscribe and wash your hands.
Hello and welcome back to my podcast. I know more about movies than you do. Don't forget to like and subscribe. Today we're going to be looking at clips from the classic Cool Hand Luke, featuring star of Salad and Screen, Paul Newman.
In the movie, this guard's famous glasses are convex. They reflect light to create virtual, upright images of the inmates. The further the prisoner is away from the guard, the smaller the image is.
The director uses convex mirrors as a visual cue to explain how the guard sees the prisoners.
Let's quantify what the director was trying to show. The guard's convex glasses have a focal point of 20 centimeters. A 170 centimeter tall prisoner stands 100 centimeters from the glasses. What is the image's location? We know the focal point because it's convex. It's not just 20 centimeters, it's negative 20. We know the distance of the object. We know the height of the object, but we need to know the distance of the image. This is another way of saying the image's location. I want to find di. There are two formulas. I see dou and f. Di, dou, and f all go together. Write out your formula, plug in what you know. Fractions are messy, so turn those fractions into decimals. Use your one-step equation to solve. This gets you 1 over di. In order to find out what di equals, you either need to use the inverse button on your calculator or divide negative 0.06 by 1. My final answer is negative 16.67 centimeters. This means I have a negative distance from my image. That means it's a virtual image, which confirms that all convex images are virtual images. Now that we know all that, we can find out how big the image is. We want to find the height of the image. I know there's the formula, hi ho, di do. This is my magnification formula. I write out my formula and substitute in what I know. I need to do a little cross multiplication. 170 times 16.67 equals hi times 100. Divide both sides by 100, little one-step equation, and then I get the height of my image as 28.34 centimeters. These convex glasses created a virtual upright image that was smaller.
The prisoners not only appear as virtual upright images to the guard, they also seem to be smaller. The images have a smaller height. He sees them as less than him. Thank you very much for joining me live from my parents' basement. This has been I Know More About Movies Than You Do. Hello and welcome back to Making It Up, the makeup tutorial show where I have no idea what I'm doing. Today we're going to be using some makeup and a makeup brush, but most importantly we'll be using this concave mirror. Now right now this concave mirror is creating a real inverted image of my eye. It's not very helpful to have an upside down image. So I need to move closer. As I move closer, I hit the focal point and my image disappears. I can't see myself in the mirror anymore. As I move even closer inside that focal point, I can start to see that I've created a virtual upright image. So now if I wanted to do some eye makeup, I can see myself with a bigger image. I'm almost zoomed in. Well now, let's make ourselves pretty. Ow!
You can't be pretty if you don't understand the math. So let's look at the focal point. Your face is 40 centimeters from a makeup mirror that has a center of curvature of 50 centimeters. We know the center of curvature. We want to know the focal length. We know the relationship. Focal length is half center of curvature. Write out your formula. Plug in what you know. Half of 50 is 25 centimeters. So our focal length is 25 centimeters. Now that we know the focal length, we can find the image's location. There's our focal length. There's the distance of the object. That's how far your face is from the mirror. And now we want to find the distance of the image. That's another way of saying the image's location. Write out our formula. I'm dealing with dou, f, and I'm solving for di. Write it out. Plug in what you know. Turn those scary fractions into decimals. Solve the one-step equation. And then the most common wrong answer is 0.015 centimeters because you need to take the inverse. This is 1 over di. I want to know what just di is. 66.67 centimeters. So this image is pretty far back. You'll also notice that because you're outside of the focal length, you get a positive di, which means you have that real image. It's in front of the mirror, not behind it. When we moved inside the focal point, we ended up with a virtual upright image. The 30 centimeter tall face is 10 centimeters from a makeup mirror that has a focal length of 25 centimeters. We want to start by finding the image's location. So we know F, we know HO, we know DO, and now we want to find DI. DI, DO, and F all go together. There's our formula. Write it out, plug in, turn those fractions into decimals. Subtract to solve for 1 over di. But remember to take that inverse. You can either use that inverse button on your calculator or take 1 divided by negative 0.06. That negative di, because I'm inside the focal point, reminds me that I have a virtual image. That image appears inside or behind the mirror. Now that I've found my image's location, I can find its height. I'm going to go for high over ho, di over do, write out the formula, plug in. We got to do a little cross multiplication. Divide both sides by 10, and you get an image height of 50 centimeters. This lines up with what we saw. We saw a bigger eye, so I could put my makeup on a lot easier. Once we know all this information, we can look at the magnification, because no one looks prettier than when their face is blown up to magnified proportions. We're looking at this formula. High over ho and di over do individually give us our magnification. I'm going to try all of them. High over ho, di over do, 50 divided by 30 gave me 1.67. 16.67 divided by 10 also gave me 1.67. That means in this case, my eye, or my whole head, would appear 1.67 times larger than usual when my face is inside the focal point of that convex or concave mirror.
Now see, with the right focal point and enough practice, you too can look beautiful.